We have been overwhelmed by your response. Many people have posed the Optica question direct to my team and I. They know what we do for them. But what can active leaders in optics and photonics do for us? The answer is simple. By joining Optica as a corporate member, you encourage us to expand our trusted global network and support our new range of services. Get deep insights into what's next for your sector in photonics with free access to over 90 market reports, plus exclusive access to the PowerPoint slides for the in-person meetings. And corporate members get exclusive access to all Optica industry meetings in 2024, including the VIP reception during Photonics West, or Executive Forum during OFC, the Freeform Optics Industry Summit in Rochester, New York, hosted by Optimax, the Advanced Manufacturing Industry Summit at SUSE Micro-Optics, the special events at ECOC in Frankfurt, the third PEC Summit in Silicon Valley, the Optica Laser Congress in Osaka, Japan, plus the Optica Quantum Industry Summit, this time in Bristol, UK. And remember, being a corporate member of Optica also gives you discounted access to many partner events such as PEC Summit Europe, Driving Vision News, and PEC International. Hello, before you shut down for the holidays, grab your calendar and mark it for Tuesday 16th of January for the next online industry meeting. Of course, it's earlier in the month this time because of the face-to-face meetings at Photonics West. The theme on the 16th is quantum computing. There are currently several approaches to quantum computing and all of them involve photonics in some way. Lasers for trapping ions, spectrometers to characterize cool atoms, or integrated photonics for creating and manipulating qubits. From the Quantum Industry Summit at LIGENTEC, we learned that the main challenges are threefold: highly efficient and miniaturized single-photon detectors, narrow linewidth laser diodes, and photonic packaging with the lowest insertion losses ever. Because, and I will never get tired of saying this, in quantum, every single photon counts. To answer the quantum Optica question, what can every single photon do for quantum? And what can the quantum industry do for photonics? The following experts will be in the room. But remember, you are all invited to come and voice your challenges, needs, and technology capabilities. Join Puja Diana Tanay and Valerian Gies, Quandela, Laura Nugent, Quantinium, Polan Imani, Icarus Computing, Peter Null, Inflection, Christine Bond, Photonic, Maxine Sieg, IGIC, Jelmer Renema, Quix, or Catherine Simondi, ID Quantic. And to support their needs, some of our corporate members will share one slide, and those are Optica, Lyonics, Advanced Microfoundry, AMF, Modulite, Hamamatsu, Menlo, or Keystone Photonics, among many others. You are all invited. Everyone in the Optica corporate engagement team has worked very hard on this. And they are all waiting to start. I can't wait anymore. Let's go live right now. Finally, we are all here at the Quantum Industry Summit online. We have worked really hard to bring all of you together, and on the next 2 hours, what we're gonna do on the next 2 hours, you know what it is to find ways of working together. It was fantastic Christmas, and now we're back, and it's snowing dramatically heavily here in Washington DC, and I'm pretty sure that when we go to Modulite, they're gonna tell us that they're gonna be like minus 18 degrees or something. Let's start with a fantastic meeting. But first, let me introduce myself. My name is Jose Pozo. I'm speaking on behalf of Optica, the former OSA. Optica, the leading platform for photonics and optics exchange. And I speak on behalf of 184 employees, and the corporate engagement department has now 549 corporate members. Thank you so much for your support. What we do for a living is very simple. We find ways of you working together, and these are the people who tell us what to do. So if we make any mistake, blame our corporate engagement council. Amy, Esquito, Michael Levy, Reinhard Walker, you know who they are. They are the ones telling us in which direction we should drive the Optica Photonic Industry Network. But today is all about quantum computing. Quantum computing in every single way, ions, superconductors, photonics, all of the platforms need lasers, detector, integrated photonics, need the photonics industry. And we are here to try to solve it. What we do, you know the format. What we do is we have a set of companies who are here with challenges, and a set of companies who are here to also with challenges, but also trying to help the challenges of the companies that are being presented. Let's see if we can do the mix and match that we like so much at Optica. I am overwhelmed. We are overwhelmed. Puya Dianat, Carmen Paños, the entire team is overwhelmed by the amount of companies registered for the meeting today. We are 491 people registered for the meeting, both in YouTube and in the room. I am amazed. Everybody who says quantum winter is coming, this is quantum Christmas. Thank you very much, all the companies here. Remember, we understand every corporate member, and we always position them in the supply chain. This slide in front of you has been published in LinkedIn and will also be part of the report after this meeting. I also would like to remind everyone that today we start our new season of online industry meetings. 27 February, mark it in your calendar. It's about new space. We want to understand the needs of the space agencies or the space companies and match it with the technology of our members. 27th of February, new space. Very interesting for many of you active in QKD. But let's continue today and remind everyone that if you go to optica.org/market reports, we have our latest quantum report there and many others. Optica.org/market reports. All the market reports there are for free for all the corporate members. Thank you very much for your support. And the last thing I'm going to tell you is that this meeting is also live streaming YouTube. So I hope you're looking your best because it's going to stay there forever. Hello, YouTubers of the world. Thank you very much for joining the meeting. If you have any question, post it in the chat and I will read it in the room. And that's, of course, also valid for the people with me in the Zoom room. If you have any question during the meeting, please put it in the chat and you will have the chance to voice it. I think it is time to start. Puya Diana, are you ready? I'm ready. We're going to start.
I'm ready.
With
let's start.
You know, Puya, I have been doing this job for quite many years, and I was running another association before that. Many people know this, and we didn't have any quantum companies. And eventually, a company from Palaiseau, from France, two people, very handsome guys, joined, and they were the first quantum company that joined that association. Now we are here with many companies in an optics and photonic industry because of that brave move by Quandela. Valerian Gies, thank you very much for being such a good friend of mine. Thank you for being a corporate member of Optica, and thank you for opening the Quantum Summit today. The floor and the attention of everyone goes to Palaiseau, goes to Quandela.
Hello, thank you very much, Jose. Thank you, Puya. It's really my pleasure to be here tonight, well, this morning, this afternoon, I don't know wherever you are, and to open this session. So let me take one moment just to share my screen. Should be okay. So thank you very much, Jose. You have been following the journey of Candela since 2017, 6 years ago already. At the very beginning, we were building only single photon sources, and now Candela designs and builds useful quantum computers to drive society and industry quantum transformation. So I'm Valerian Gies, one of the co-founders of Candela. I'm very pleased to be here to present and to introduce Candela, the roadmap, the product, and also to have some exchanges with some of you. Very briefly, the hair technology of Candela that I mentioned already. This is these devices that you can see, electronic microscopy image, unique device that's the brightest, the most efficient that you can find around the world. This is now ready to be industrialized. We have invested in our own clean room in Paris region, in Palaiseau, like Jose mentioned, to start the volume production of these devices. And this, what it is? This is the brightest, the first near ideal single photon sources. How? Why? It's because we can deterministically fabricate quantum dots inside an optical cavity that you can find here. Well, you can see here. And with this, you can control the qubit, which is inside the cavity, which is inside the quantum dot, and you can generate high quality, pure single photons to run quantum computations. And then we are already thinking about next generation of computers by using the spin inside a quantum dots. Unfortunately, I will not have time to go there, but just for you to notice that this is actually a unique building block which will make quantum computers a reality. What about Ascala? Ascala, we are very proud of Ascala. This is our first big quantum computers, which is actually open to all via our cloud. We have spent a lot of time in order to develop our first cloud system, so which is fully accessible in cloud.candela.com. And if you register just with your email, no need to big stuff, you can then have access to Ascala. Ascala, how is it made? Basically, this is a single photon source. You generate the photons, and then you take all these photons sent into parallel channels connected to a universal interferometer that can be controlled via our software. And everything is available in the cloud. We have already about 500 users of our Candela cloud from all around the world in many continents, North America, in Europe, Germany, France, UK, Italy, everywhere, and also in Asia, Australia. We have customers from all around the world. This is an open to all platform without any restriction, without any limit. Everything is accessible and controllable via Perceval. Perceval, this is an open source programming framework that we have released about 2 years ago. This is completely open source. And with Perceval, it's possible to train yourself to simulate quantum circuits based on photons on CPU. And now it's also possible to do it at larger scale on GPU with the best state-of-the-art NVIDIA chips that are available in the world. And with the same software, no need of change the big things, then you can run your program and execute them on a real quantum processors unit, which is available which is hosted here in France. Perceval was elected as one of the best and more user-friendly framework by Quantum Zeitgeist. If we compare and we look at the different benchmarks, the metrics, and the quality of the computation what was done at Ascala, of course, there are many things to be done. First metrics that we can already talk about, it's the gate fidelity. Well, actually, it's not only about the gate fidelity because we didn't want to split between different the state preparation and measurement fidelity. So actually here, everything included, we have these gates plus preparation state measurement and measurement fidelities all combined end to end. And with this, actually, we are at the state of the art if we compare these gates with this fidelity with all the other platforms that are available in the world. Plus, we have demonstrated that we can generate a heralded GSZ state, which is actually a unique, useful resource that's going to be necessary in order to scale up to build measurement-based quantum computers. That's going to be the next generation of quantum computers. That's going to be a step forward to bring us closer to the useful applications. I will not enter into more details. Be aware that all the performance and technical information are available in arXiv, and the paper will be published. It's already accepted in Nature Photonics. Just a word about the fact that, there is a possibility to connect, to get access to a lot of tutorial videos. Why we did all of this, why we have wanted to have these quantum computers available in the cloud, because we want users, we want people to use them, to test and train themselves to develop new applications on these platforms. So there's a bunch of tutorials videos that are available on Candela YouTube account. And please be aware that actually now it's possible to simulate at larger scale with dozens of photons on larger photonic chips on GPU chips, NVIDIA 800. And then in the coming months, we will be releasing new quantum computers in more modes, with more photons and larger quantum processor units. And then finally, we have succeeded in building and delivering our first HPC high performance computing ready quantum computers. So we have fabricated one machine, which is actually here in the center of the image, and we have delivered this machine into an industrial data center, which was not designed and done to host big quantum computers. But for them, it took us was easy to bring the machine, plug it there, just as simple as this, and run it. So this is also due to the fact that we have worked a lot on the engineering. We have developed a design which is upgradable because we work with modular blocks that are all connected by optical fibers and with semiconductors. Quite low energy consumptions, less than 3 kilowatts. If we compare with the big dilution fridges that you can find on the market, actually it's much more energy efficient in terms of in order to help customers to actually not spend thousands of dollars in euros in energy. So this first delivery was done at OVH Cloud, which is actually a French data center provider in France, in Europe, and was done in October 2023. So we have succeeded this first step, and we are actually already running and working to deliver the next data center customers. So this is all for Candela. Thank you very much for your attention. I will be pleased to have some interaction. Don't hesitate to contact us. And also please be aware that we will be at Photonic West. So we'll be happy to have a discussion and a chat or on a coffee and our booth. Thank you.
Thank you very much. Hands up. Who will be at Photonics West with Valeria and me? Great. Many people. Of course, Clea has to be at Photonics West because otherwise I would cancel it. We have a few questions for you, Valerian. Thank you very much for that. The first question goes all the way to Seattle area, Castor Optics. Kathy Vedette, tell us what's on your mind.
Hi, I actually did not have a question. It just went automatically when I raised my hand because I will be at Photonics West. So, but thank you for the shout out.
Tell us in one sentence, what does Castor Optics do and what brought you to this meeting?
Yeah, so I'm here to learn essentially what quantum computer is doing and the role of photonics and probably fiber optics components, how we can help you with this development. Thank you.
Thank you very much, Kathy. Fiber components from Castor Optics, raising the hand every time she's asked. Let's go to Alpine Research Optics. Kestutis Juskevicius, you have something in mind. Share it with us.
Yeah, hello everyone. All this quantum computer looks great. Could you elaborate on let's say top 3 problems you have to build these computers, rather technical or fundamental? Thank you.
Yes, thank you very much. Many challenges in front of us. So just brief answer, and hope we will have an opportunity to discuss further later. Losses. Actually, photons are very robust and resilient to noise. The main problem with decurrence, which is the main advantage of photons compared to other platforms like ions or electrons. The main problem with photons is you can lose them very easily. So it can be absorbed, it can be scattered by the different components. So we have to work a lot of this. So transmission is a key to develop useful and efficient systems. This is also why the fact that we have super efficient single photon sources is the main advantage of Candela. And then the other key development that we are running, where we are investing a lot of efforts, is how to fabricate fast modules. Because we need to implement feed-forward, we need to implement fast actions on the chips, on the photonic integrated circuits, on modulators, on demultiplexers, and we are competing with speed of light. So we need to have devices running at gigahertz.
Thank you very much for that, Valerian. This is half of the Optica question. This is what others can do for you. What can you do for others? Quandela, you presented today, you have a platform ready with some qubits available. How the people, the community, how can they access this computing power?
Yeah, that's a good question. So why I made the choice to present this? Because I want to convince people that it's already available for people to deploy, to test, and to run, test how to make some calculations with photons. I didn't have time to go further into the details about the different applications, but for example, it's possible to run some quantum machine learning algorithm on our platform. It's also possible to develop some chemistry algorithm on our platform, quantum random number generation for encryption, cybersecurity, many applications that are available. So don't hesitate to connect and see all the different applications.
You have made a difference in the efficient single photon sources with quantum dots. This is a meeting which we want to showcase the technology of our members. So I'm going to introduce you to somebody who you already know, but it's a person who we have been quite amazed at Optica. They are commercializing the quantum dot technology of NIST. This company is Icarus Quantum, and it's presented today by Pulan Imani. Pulan, thank you very much for being with us today. You have one slide to showcase today after Quantela. Tell us, what do you do and how can others help you?
Absolutely. Yeah, thank you for the intro and for the invite. This is truly a pleasure to speak at an Optica event and as a corporate member now. So yeah, I'm going to tell you about Icarus Quantum, and we're a spin out from NIST here in beautiful Boulder, Colorado, and we're making entangled photons, efficient entangled photons, and we're aiming at scalable quantum networking. So the technology that we're using is same as what Quandela and Valerian use, 3-5 quantum dots, and these platforms, as Valerian said, they year after year shown the highest efficiency in single photon generation. And now we're using these to generate entangled photons efficiently and on demand. And what we're looking at first is the cybersecurity that quantum networks bring. And then the holy grail of this technology is going to be connecting quantum computers in a modular way to each other and then perform distributed quantum computing. We have some sponsors, mostly from the US government, the Air Force, Space Force, NASA, and NIST. And we have some academic partners. And last but not least, I do want to emphasize that in Colorado, there's been a lot of quantum activities going on in past few decades. And now Colorado was just picked as one of the 2 quantum tech hubs in the US by the Department of Commerce. And that is, we have this consortium here, Elevate Quantum, and the excitement about quantum in the region is only going to get bigger and bigger. So
we love Colorado. Last year, Optica had our Quantum 2.0 conference there, and we have many companies in Colorado that are doing great job, like especially, for example, Quanta. Thank you very much, Icarus Quantum, for joining, and I'm coming to Colorado very soon to see you. But let's continue. Today, we have many interesting companies in the room who are looking forward to start new cooperations, and the next one is a company that brought quantum to the consumer market. If you went to the Mobile World Congress last year, you could see a chip from ID Quantique. We wanted to understand what they do in the field of quantum computing. So today with us, Felix Bucieres is telling us a bit about IDQ in quantum computing.
Great. So thank you very much, Jose. I hope you can hear me well. It's a real pleasure. Yeah, perfect. So it's a real pleasure to be here. I'm really happy we joined the Optica as a corporate member. It's giving us great opportunity to connect with you. So I want to tell you about what we do. So one of the things we do at IDQ is to enable quantum connectivity with photons. And we've been focused a lot since 22 years in delivering single photon detectors. We've been on the SNSPD aspect of things since 2017. So our focus is really on proven high performance. Of course, innovation, we have to innovate, and we've been doing with a lot. Short lead times, high quality, and reliability. So a bit more about some of the technology itself. In quantum computing, one of the very important aspects you need from the single photon detection part is photon number resolution. And we've been quite innovative on that field, and we've been delivering some of these since 2021. We have a device that can reach very high end photon efficiency with a single coaxial line. So it's also efficient in terms of using the number of spots you have in a cryostat for SNSPDs. They can also reach very high detection rates, work with the CW regime or pulse regime, working at the very relevant wavelengths, 1550, 920 for quantum dots. And this line of detectors is continuously evolving. Just to finish off, I want to say that we're going to be launching this year or shipping this year a fully compact rack-mounted system with lots, fully autonomous operation. We call it the Pro system because it's really for the most professional applications. So we're quite happy to be telling you that today. And then, to the questions, what you can do for us. So we want to partner with you. We want to understand what are the system features and detection features that will be leading to meaningful R&D opportunities, but also business for you. Okay, so this ability to talk to you is very precious. We want to be getting the best out of it from both directions. And then the other direction. So what we can do for you is to discuss about scaling together, both from the technology point of view and operational point of views, which is where the field is going. And that's, we'd be very happy to engage a discussion along those lines with all of you. Thank you.
Thank you very much, Felix. Let me remind everyone watching live in Zoom and live in YouTube, if you want to get in touch with any of the participants today, because you can address any of their needs, all you have to do is send us an email, jpost@optica.org, and we'll make the introduction for you. This meeting is about creating business. The next person, do you have a question, right? Clea Dimitri, all the way from Hamamatsu Photonics. Tell us, the floor and the attention of everyone is yours. You have a question for Valerian, I think.
Oh, no. Yeah, it's kind of connected to my slide, but I know Valerian kind of brought up a really good point about, the losses. So I was kind of curious if he has any insights of like, as you design these systems to be larger, like how can you kind of try to mitigate those losses across all the components? That was kind of my question.
Yes, let's go to the slide and we'll address the question.
Awesome. Okay, great. So let me just quickly share my screen here.
Corporate members always have access to share one slide at our industry events. Thank you very much, Hamamatsu, for being one of our oldest members.
Sure. Yeah, so the tagline of Hamamatsu, and I think the direction we're trying to go into, is we're trying to help people seamlessly build these quantum computers. So what are our current capabilities? Today we have a lot of detector and imaging options to really help people identify optimal solutions as they build these computers. Some things that people may not know is we actually have a rapid design group. They basically can rapidly develop prototypes with some of our solutions to make them more easier to interface with your the systems you may be making. And we've actually shown some really nice success with our cameras recently on this. We're also vertically integrated, which can help us think of any custom solutions that you guys may need in the future. And the challenges I kind of put here, they're kind of pretty big ones. I think Hamamatsu is involved, but of course, I think the whole industry may need to tackle this. I think the first one is like, there's a bit of uncertainty of what new solutions will be needed and when, as you're trying to go to the scalable, universal, fault-tolerant quantum computer. Another big one is what is good enough, especially for systems design. I picked on PICs here a little bit because it's a hot topic, but that's expensive, high volume. I know there's some PIC players, so it may not be a challenge by the end of it, but definitely just thinking of return on investment for these manufacturers and the reliability as well. So how kind of what is needed and what aspects of the computers. And then lastly, I think this is a big one, and I think Valerian from Quandela really hit on it, is like all these solutions today and in the past were really developed in isolations of each other. But is there any ways moving forward that we can consider them to help really these systems engineers build better systems as they scale? So, is there any way these solutions can start talking to each other so we can basically make a more seamless and sort of reduce a lot of the engineering challenges that people face? So thank you very much.
Thank you very much, Clea. Could you repeat your question for Valerian regarding the losses?
Sure. Yeah. So I think Valerian really touched on this. So this last challenge here, I was just kind of curious, Valerian, like how are you kind of tackling this sort of challenge of losses, especially across components? And is it, what solutions do you potentially see potentially happening, or what is something you would like to see from the community, or something that would help you kind of address that more head on?
Thank you, Clea. A very nice introduction, actually. So basically, it's a general problem, because for the end-to-end efficiencies given by the transmission from every connections, now we are not in a maturity where it's possible to have everything a monolithic device, because it's not scalable, and we need to build on devices that are modular, connected with fibers, and with modulators as well. I see that because you can provide modulators. Now, the fact that I see that there's kind of trade-off between speed and transmission of modulators. But to build a fault-tolerant quantum computers, is no doubt that we will need both, actually.
Valerian, we started with you at the success story of the photonics, and now we move to another success story. This company, part of Optica, has impressed us because they talk about spin qubits with a very big vision on scalability. Christine Bonnet, thank you very much for being part of this meeting today. The floor and the attention of everyone goes to Photonic Inc.
Hi, can you see my screen? I'm going to try to put presenter mode on. Is that
Crystal
good?
clear. Yes.
Great, lovely. Hi everyone, I'm Christine Boone. Today I'm going to introduce Photonic Inc. and I'm going to talk about how we use photonics as well as silicon spins to build our quantum computer. So to kind of get us started, just to give everybody a little context for the quantum computing industry in general, we're kind of in this predominant design era. So there's a bunch of different quantum computers. There's a bunch of different ways to build a quantum computer. Pretty much need something that can hold some superposition, and you need something that you can entangle different pieces together. So those are the fundamentals for what you need to kind of start building a quantum computer off of that. With other types of technology, we enter an era where we kind of see dominant designs emerge. This is not where we're at. We're mostly just kind of watching the scene and seeing how things kind of progress. But for example, here with cell phones, there's a bunch of different ways. I don't know how many flip phones or these big blocky ones everybody had, but eventually we kind of got to the iPhone, and then ever since then, every kind of cell phone looks the same. So just to kind of give us a general idea of where we're at with the industry, we're in this predominant design era, but we are closely approaching this kind of dominant design emergence. So what we do at Photonic Inc., we're a company that's based out of Canada on the West Coast, and we're using this interface between silicon spin and these silicon photonics. So our silicon spins, the spin of these atoms is holding the quantum state, and then we're having telecom wavelength photons interacting with our system. So in this way, we can build a distributed and network quantum computer very easily and naturally because our silicon spins are emitting at the telecom wavelength. So we get both the stability from silicon spins and the manufacturability from silicon spins, but then we also get to utilize the photonics of it so that we can actually have these distributed quantum supercomputers. So just to kind of walk through this a little bit, sorry, I'm going to cough. So we use something called the T-center. So in each of our T-centers, we actually have 4 qubits. So the electron is the one that's emitting the telecom wavelength, and then the carbons can hold the state for a very long time. And then we also have this additional hydrogen spin. So when we're looking at this, we can actually build the quantum network from the quantum computer. So the T centers are acting either as a quantum computer, like a network quantum computer, or we can actually use it to build a quantum internet out of. So our technology is actually both quantum computing and quantum networking. So then, yeah, we have optical switches and detectors, but we're at about 1 Kelvin, so it's quite cold. We do need to have these dilution refrigerators, but it's not as cold as some other types of quantum computing. And then sort of longer term, as we look at this, it's about creating a distributed quantum computer. So we could have a bunch of these cryostats, a bunch of different chips that are all interconnected. So like each chip could have X number of qubits on it. And then by having a ton of those systems in the same room, by having all these photonic interconnects, we can scale up the system very easily. And then with that said, we can also start looking at these metro scale fiber links, or actually using satellite links to create something like a quantum internet. So what does quantum at scale mean, and what are we kind of working towards as an industry? So generally, quantum computing, as many of you have heard probably in the past and also today, there is this potential to address some of these global issues, right? So there's this potential, and it's kind of like where we were at when a digital computer took up an entire room. We couldn't really predict that Facebook was going to fall out of it, but all of these applications to the internet and to digital computing couldn't really be foreseen. So we're all kind of in this industry building these quantum computers and really excited to see how they're going to be used. And I think that's also a large part of why all these quantum computing companies are here today, is that we're all looking for partners, right? We're all trying to understand, how would you use a quantum computer, and how can we start looking at developing these algorithms and these applications. And then quantum networks, they can connect and scale quantum supercomputers, and then also enable other types of applications, and then generally working with quantum workloads. So with our technology, we're scalable. Silicon is very manufacturable. It's very easy to make more qubits, put more qubits on a chip. And then we can also have this distributed network of quantum computers that are all interconnected with these telecom wavelength photons. And then the other thing that's great too is because of the telecom photons and the connectivity that we can set up, we can also look at more efficient quantum error correction codes. So because quantum systems are intrinsically error prone, you need something called quantum error correction. And because of the way our system is set up, we can actually start using these really efficient error correction codes. Anyways, that's all. Any questions?
Thank you so much, Kristen. That was great. And actually, I start with one question. So I would get a little bit more specific. What, in terms of like what you said, you're looking for partners and basically getting involved with the ecosystem. What are the kind of partners? What sort of photonic components? Is it the manufacturers? What exactly are you looking for?
Honestly, all of the above. I think there's a ton of experts in our company in photonics. Unfortunately, I'm not one of them. My PhD was in quantum error diagnostics, so I can talk about that all day. But I do think we're looking for partners generally to also look at algorithm development, but also to understand more efficient ways of working with our photonics side as well.
Okay, and that's a good point you mentioned, the algorithm development, which actually brings me to our next speaker, Inflection. So many of you know Inflection as being a quantum computing company, but they have a diverse set of products, and one of them is actually the algorithm. So Peter Knoll from Quantum is from Inflection is here. Peter, why don't you start sharing your slide?
Yeah,
and explain more.
Thank you. Yeah, great to be here. Great to meet everyone. My name is Peter Knoll. I'm from Inflection, from the Chicago office. So quick background on Inflection. Inflection started in 2007 as Cold Quanta, so you may know us by that name. by Professor Dana Anderson at the University of Colorado Boulder. And now we've grown to have offices in Boulder, Austin, Texas, Chicago, Madison, Wisconsin, Melbourne, Australia, and Oxford, UK. So in short, what we like to say is that we do is we shoot lasers at atoms. So we do a wide range of the quantum ecosystem type products, two of which are shown here. Had to keep it short today and focused. So we do everything from quantum computing. You see our quantum computer called Hilbert there, to quantum sensing, quantum RF, quantum atomic clocks, and we recently launched in December publicly our quantum matter machine, Octant, where you can make Bose-Einstein condensates over the cloud. So our technology isn't a photonic quantum computer per se, but it is a neutral atom quantum computer that depends a lot on lasers and on photonics because of that. So it's all based around this core technology of glass vacuum cells. So that's what Hilbert's based on. We think this approach is highly scalable, and I think there's more evidence of that as each month goes by in the industry. Neutral atoms are all identical by nature, so that's one fewer imperfection as we scale up there, and also no cryogenics, just lasers. So while the lasers do have their advantages, that's one of the challenges we're facing today and looking for solutions is improved laser quality, as well as laser quantity. So we like to say now that we're taking quantum out of the lab and into production. We recently announced plans to build manufacturing capability in the state of Texas. So we're looking to build not just one quantum computer or quantum optical clock here, but hundreds and thousands in the coming years. So it's a priority for us to invest in laser technology that's more reliable, out of the box works, and is scalable. So and just I know today is mostly focused on quantum computing, but just to mention our atomic clock ticker, which is available for pre-order. Ticker Prime is the model right now that gives hydrogen maser-like performance, and is rack mountable and somewhat ruggedized. But as we go forward, our photonics roadmap is going to be very important to get the size, weight, and power down to chip scale, reduced to pick size. You can see future plans for ticker blades. So we're looking for ways to advance that roadmap. So if you have any questions, drop them in the chat or speak up.
Thank you so much, Peter. And and again, the question is what you can do for the industry and what industry can do for you.
Yeah, so what we can do for industry, we have this broad portfolio of these quantum technologies. So I think those are out of the box, ready to use. For example, with Ticker, we believe there are applications there to unlock almost new markets with applications in data centers. So instead of having to build a new data center or lay more fiber to increase the throughput of a data center, we think these clocks can be integrated locally into the data centers to increase throughput. So
it will be interesting. Yeah, just
so sorry. So that's an example of what we can do on the clock side. Hilbert's a little less far along than Ticker in the product life cycle, but we have plans to similarly produce not just one version of Hilbert, but several hundreds, hopefully in the future. And as far as what industry can do for us, we, like I said, just improved laser quality and reduced size, weight, and power, as well as improved quantity, because you can only get your hands on so many of these at the moment.
All right, and I see questions are coming up through the chat. I have a question for Christine from Kurt Stockbro from Sparrow Quantum. Kurt, why don't you put your camera on and ask Christine the question that you posted here? All right. Well,
can you
seems
hear
that-
me? Can you hear me?
Yeah. Yes.
Yep.
Yes.
Okay. Yeah, I am on my phone. Apparently, it cannot open the camera. But yeah. So my question is, I think it was thanks for the presentation. It was really nice, and it seems that the prospect of your technology is amazing. It was not very clear from your presentation how far you are with the technology actually. So what have you demonstrated now? I mean, what can you do with this color center, and how far are you from? Do you have any publications, or do you have any proof of concept of your technology?
Yeah, I can definitely comment on that to a certain extent. I don't want to. I'm not supposed to talk about roadmap publicly, but yeah. So we had a Nature paper 2 years ago demonstrating fidelity numbers and things like that for the silicon spin and the integrated photonics. Since then, we've published general papers on how the system is being developed, but we aren't publishing at this exact moment on where we're at experimentally, but that will be coming shortly.
Okay.
Sorry, that's not a very good answer, but
Well,
No.
Christian, we are all friends in here. I know you said
yeah.
you won't share publicly, but people would like to know. So maybe they can reach out to you and like have discussions.
Yeah,
So this is what we do. We facilitate for people to within the ecosystem to have private conversations. But
yeah, absolutely. And feel free to contact me for sure. Yeah, absolutely.
All right. Thank you. All right, so let's Peter in his talk he mentioned the neutral atoms and the need for lasers and our next speaker is actually the makers of these high performance lasers, Siamak Dodras from Optica. Siamak, the floor is all yours.
Oh. Thanks very much, Puya, for the introduction. Siamak Dodras with Optica, and I'm gonna start sharing my screen. All right. So as we all know, lasers are pretty much the key enabling technologies for quantum computing. And currently, many laser industries are using all sorts of technologies to meet the existing requirements of quantum computing development. For example, at Optica, we develop a broad portfolio of lasers, including tunable diode lasers and amplifiers, frequency converted lasers, fiber lasers and amplifiers, Raman fiber lasers, frequency combs, and laser rack systems for the modular integration of all these lasers in a smaller footprint. But we take the pride to cover the broadest range of wavelengths and powers, as you can see on this graph, in low noise lasers, enabling the development of quantum computers based on trapped ions, neutral atoms, photonic qubits, spin qubits, and so on. However, as the number of qubits in these systems start to scale up, scalability of the required hardware, including the lasers, become a big challenge. And a solution that intuitively looks promising in implementing such qubit modalities is implementing such modalities on integrated photonics. And the importance of this strategic shift is already recognized by several different quantum computing companies, exploring the integrated photonic platforms potentially complemented by lasers, on-chip lasers, actually. However, as we all know, this is a these are very, very early stage technologies, and there's a long way to go to achieve full-blown maturity of such complex qubit platforms. And as we navigate this new horizon of laser company, we realize that collaboration with the quantum industry is a key step towards the quantum computers based on integrated photonics. And we look forward to working with all folks here to get to that promised land. Thank you.
Thank you so much, Gilmek. And I mean, the photonic integration would require the manufacturing and the foundry. So I would like to bring our next speaker, Kavita Budaraja from Advanced Microfoundry, all the way from Singapore to here to talk about what they can do for the industry. And Siamak will get back to you to ask the Optica question as well.
Hello, everyone. Hi, this is Kavita, and thank you for this opportunity. It's great to meet everyone on this wonderful platform provided by Optica. I guess the previous presenter has to unshare for me to share. It says I cannot share the screen.
All right. It should be okay now.
So I come from the sunny land of Singapore, where I was just telling Optica and warm should come visit us sometime. I represent AMF.
I can't see your presentation. I'm not
photonic.
sure.
Oh, sorry. Sorry, just one.
Okay, no problem.
Try unsharing and resharing it.
Oh, we might have lose Kavita because I saw her drop off. Well, in the meantime, while she is trying to get back connected, Siamak, the question for you is you mentioned the challenges at early stage of photonic integration. Well, what is it exactly that you need from here's Kavita is back. All right. Kavita, we can see your presentation.
You can see my screen.
Yes.
Yeah. AMF is a silicon photonics specialty foundry. We're based in Singapore, and our main technology is silicon photonics wafer manufacturing services. And we do this at very large volumes currently for our communication customers. And we're hopeful that, like in the next few years, we can partner with some of you to also transition you into volume manufacturing for quantum computing. Everything that we do is done in our fab in Singapore. It's a 90 nanometer technology node. For us, for all the technology that we offer to our customers, our main objective is to make sure that everything that we develop is catered for their specific applications. So in the space of quantum computing, we're serving a customer base in the bandwidths from 600 nanometers to 1.7 micrometer. And for this bandwidth, we are using technology platforms or material platforms of SOI, silicon nitride on SOI, and silicon nitride on silicon. And two of these platforms, we offer them in an MPW service. And the good news is we offer these every month. So you can join them, sample the platforms, and partner with us. At the same time, as it was mentioned by several speakers in the past, we understand the importance of partnering. So we had partnered with Asanta, Photonics, and Professor Joyce Poon, where we are offering a visible silicon nitride platform also in an MPW format. If you're interested, please reach out to me. So in developing these technology platforms, as I mentioned, we have listened to our customers, and one of the device requirements that we get from them is ultra low coupling loss, high extension ratio phase shifters, size of the devices that we offer in the PDK, low loss packaging. And our latest PDK 4.0 addresses most of these challenges. We are in the process of launching a new low loss platform, hopefully where we could reach less than 0.1 dB per centimeter propagation loss on C-band. And then the rest of the platform is suitable as it is, like several of our MPW customers use it for quantum computing already, using our high-speed modulators, compact photodetectors, single-photon PDs, and many more devices. We have more than 100 devices. And all these devices are made available through all our EDA vendors shown here. So in essence, we have a technology platforms and we have all the devices ready. They're not perfect. They require a lot of improvement, I understand, but that's where we'd like to partner with you guys to take it to the next level. Thank you.
Oh, thank you, Kavita. And actually, in 2025, Optica will organize and will have an industry summit that will be an in-person event hosted by AMF in Singapore. So people get to see firsthand. I mean, that they should see it earlier than 2025. No, please don't wait till then to get in touch with AMF, but you'll see firsthand the operations there. And we are really impressed, and I'm sure you all will be very much impressed with what AMF is accomplishing. Now back to you, Siamak, just a quick question. What particularly, what kind of partner and interaction are you looking for? Just a little bit more specific on what is it that is keeping you awake at night?
I think it's
the question was for Siamak, Kavita.
Yeah.
Yeah, I think it's important to understand somehow a consensus of the what is really needed in the quantum industry in terms of lasers. And I know that many quantum industries, especially on the sensor side, they're very much looking into compact platforms, not necessarily integrated photonic space, somehow more compactized than the tabletop systems. This can be, for example, the lasers that our sister company, Eagle Yard Photonics, Optica Eagle Yard is building on chip integrated, sorry, not chip integrated, it's mini ECDLs in a 14-pin butterfly package, which is much smaller than tabletop lasers, and then that can readily be used in sensors, for example, in atomic clock. We are working on smaller versions of those, which is more compact and more modular in terms of getting heterogeneously integrated with other platforms if there is any systems downstream of lasers. But
Kavita, is that something? Sorry to interrupt. Is that something that AMF can help Optica with, like the heterogeneous integration within your platform?
It is absolutely. It's one of our top focus areas. So I guess I'd connect with them and have a chat on this.
Absolutely, and
of course.
Go ahead.
This is something that there's many hands in some integration like that. Of course, the main integration should be done or should be somehow affected by a quantum integrator, because that is something that is going to address a quantum application. We are not a quantum company. We are a quantum enabler company. We are a laser company, and we listen to quantum builders to see what they need, and we build the lasers required for that. But that, like I said, in the future, it would need a heterogeneous integration, and for this kind of integrations, we might work with many different folks. Yeah.
No, absolutely. I think we're in the same boat. We are also, we don't make any products, but we are a service provider. But this is a requirement that I do hear regularly to recommend laser sources or partners who can integrate this. So I think it's worthwhile having a discussion.
Yes.
Wonderful. Thank you both for the conversation. And with that, I'd like to introduce our. Sorry, was there a question in the room? I think I missed it. All right. If not, then I would like to introduce our next speaker, all the way from the United Kingdom, Ajik and Maxim Sim. They use hybrid integrated photonics for practical applications of quantum. So Maxim, with that, the floor and the attention of everyone is yours.
Hi, good morning, good day, good late afternoon, I suppose. So thanks very much for having me. I'm super excited to be here, and we've recently joined Optica, and straight away we got ourselves into the deep of the community. So I'm going to talk a little bit on what we are doing in photonic information processing, quantum computing, and in particular, we do everything based on optics. So We're based, actually, our headquarters are in the heart of the UK in Sheffield. We have office in London. So we built photonic quantum computer and computers networking systems with the aim of bringing out like real life applications today. And the heart of that is two things: is determinism in generation and low loss photonic integrated circuits and devices that will build out of them. So we started a couple of years ago, grown to nice size team, and we're already partnering with global leaders in different sectors, but primarily that's defense, security oriented. Was already delivering particular applications to them. So we're involved in quite a few projects. So that includes Royal Navy, British Telecom, National Quantum Computing Centre in the UK. Won a bunch of awards on our way, and with that, I would like to say a few words about kind of our pedigree, where we started. Is we already talked a little bit about photon sources and the fact that they're absolutely critical for operation, and it's on demand. But what we're also doing is we completely put them in a simple rack-mounted boxes. It's the first solution to bring in that turnkey operation on its own. And it's ready and it's been actually shipped to a couple of customers. So again, we kind of skip this, but it means that we have really, really good photons, and the best available technology today in terms of manufacturability and scaled production is 3.5s, because it also requires reasonably low temperature, almost invisible cryogenics that we can put on it. And I think one of the questions that was kind of glossed over in before, but it's the wavelengths, and that it makes it's really important because we have different platforms available to us where we operate. So there are classic quantum dots, which are in the near infrared, but we also have the ability to produce really high quality devices in telecom wavelengths, which means that we can build in the networking devices and really leverage lots of the photonic integrated technology that's available for just normal digital telecoms and interface seamlessly into this ecosystem, and also in from the application perspective in that infrastructure. So that's one of the key interesting things that we're doing. And with that, I would like to introduce you to our first quantum computer that we are unveiling later this year, but as a little preview. It's called Artemis. It's the completely field deployable platform that you can take in a data center, actually outside of the data center as well. So we use hybrid photonic integrated technology. That is, we try to combine different photonic components and materials to maximize the efficiency and minimize losses. Photonics is a game of losses, right? So it's already been pointed out earlier today. So we're shipping actually next year, early next year. If you order today, you might get one of these systems if you will be fast enough. But the size of the circuit depends on kind of configuration you're looking at. But we're going up to 32 by 32 implementations. Actually, some of the Optica members help us build them. So you see the names below, LIGENTEC in particular. I guess the reason why determinism really matters for photonics is the dramatic reduction in component size. And this is where we're heading with this, because you can reach utility much, much faster with smaller number of components and actually smaller systems, which are doing some practical applications on. And I'd like to touch on a couple of these things that we're doing. So in terms of like what we're doing, what we're looking for as well. So we are building quantum computing systems and applications for them. So we can supply you with systems with components such as photon sources for whatever research you're doing. So we're also looking into the application space, and in particular, we're interested in how we can leverage more near-term solutions there. But we're very much open to also collaborative research, as well as improving the efficiency and the scale, the size of the systems that we make. Few things on ours, but I think you'll see these people appearing in different areas within Optica. So it's not just going to be one face. So please do, if you find them, have a chat. And some of us might be actually at the Photonics West. So it would be great to meet whoever is there as well. And please do get in touch. Thank you.
Thank you very much for a great presentation. Thank you for all your support for many years. It is great to have you at Optica. For you is the Optica question. What can you do for others? What others can do for you? A couple of challenges you still should address in the coming year.
So, of course, I think the major challenges remain in photonic integration or complex integration of different materials together. So on top of the efficiency of obviously devices and losses per, say, lengths of the device. So those are kind of major research programs that we are already involved in and looking to develop. So that's probably, from the tech perspective, is one of the biggest challenges out there. Is actually making sure that we hit the right specs, because still it's very, very demanding in terms of losses.
Thank you, Sunil.
Many people actually would like to help you, but we have one question in the room coming from the company OE Waves. OE Waves is one of our members in microwave photonics. Ori, welcome to the meeting. What's on your mind?
So yeah, we've got a couple of things that I'm wondering about. One is in your photonic computer, do you run into issues with laser stability? Is short-term or long-term stability more of an issue for you in terms of noise? And of course, the long-term survivability of the laser is an issue, but just thinking about the noise right now. And then also another question is other applications for the fundamental technology that you're developing. Are there other things that it could be used for other than quantum computing?
Well, I'll address the stability because that's a quick one. I think the short-term stability is the hardest to deal with. I mean, long-term drifts, you can offset them. There's some reasonably easy way to do this. So short-term noise is more problematic. We use some lasers inside, and that is which we don't make. Some of the partners who make them are in this call I've seen. So in terms of applications, that's a blessing and a curse at the same time, because you have set of applications that go from quantum metrology and doing things like cancer diagnostics with microscopy, all the way into like quantum internet, generating like large entanglement states, and even QKD, space-based communication. So we have some play in those areas, but that creates an extra challenge in general for, to be honest, just specific to us, but in general in quantum market. That's where it's heading. And yeah.
Thank you very much, Max. Stay with me because I'm coming to you for a bit, but now I would like to address a couple of challenges in supply chain. We're going to go to a beautiful city in the Netherlands, Delft. And we have there Eitan Oxenberg talking about single photon detection, single quantum. Tell us what you can do for others, what others can do for you. The floor is yours.
I thank you for the introduction, and it's very nice to be here. So my name is Eitan Oxenberg. I'm part of the research team here in Signal Quantum. And at Signal Quantum, we make basically single photon detection solution based on superconducting nanowires. We've been doing that for more than 10 years now, starting as a spin-off out of Delft University. And as you can see by the spec sheet here, we're really providing state-of-the-art solutions on system detection efficiency, but also temporal solution in noise or dark counts and a very wide range of wavelengths. And recently, we've also introduced some customer-inspired solution. This is something we like to do. We like to engage with our customers, understand what they want, and then make it. So you can see here the fully rack-mountable solution, or the interleave detector that can provide ultra-high count weight for quantum communication, for example, and photon number resolution capabilities that are important to some quantum computing platforms. But this is all pretty standard, and you can find all of this online pretty easily in our website. But I'm here specifically from the research department because we're really trying to pay more attention to the quantum computing market. And we're trying to engage with the companies, understand whether their photon detection needs, basically, so that we can provide their optimal solutions now, but also in 2, 5, and 10 years. So we want to align sort of our roadmaps together so that we can offer the best solutions also going forward.
Optica, question for you. What can you do for the others? What others can do for you?
Yes. So obviously, as you know, providers of these superconductor based solutions, we're looking for people who are interested in incorporating these type of detectors, these type of specs, and we want to cooperate with them in order to, you know, address all the challenges that were already talked about. As
beautiful item. Let's go to Max. Max, you have these single photon nanowire detectors, possibly on chip. What would you need single quantum to do for you to be able to integrate those?
Well, we probably need to sit down and talk a little bit more in detail on how exactly we're going to do. There's a process we are looking to develop in terms of like different chip integration in the coming years. So I think it will be a good time, and I believe some of our technical teams might be talking on the opportunity, but don't hold me accountable for that.
So we all know that what makes PsiQuantum special, that was that they managed to integrate the nanowire detectors on chip, and now Single Quantum is coming here to offer this to all the companies in the photonic-enabled quantum computing domain. So Eitan, be prepared because there will be many introductions after this meeting. Max, back to you. Tell me about 1 or 2 challenges on laser diodes.
You mean on our product sources?
Power, yes. No, laser diodes.
Yeah. So actually for us, we prefer not to use them exactly because they are so challenging. So we still need like proper lasers. But if somebody can come up with a good, really sharp laser diode, they can do something like a sub-picosecond or maybe 5-10 picoseconds. You know, there's a really interesting conversation for us to be had.
Let's see how close we can get with the people in Optica. Let's go all the way to Finland, to Tampere, minus 18 degrees C. Please allow me not to say it in Fahrenheit. Kalle, thank you very much for being with us. Tell us what you can do for Max and the rest and what they can do for you.
Absolutely. So you should be seeing my screen shortly.
It's frozen. Now it's here.
Yes. So hello, everyone. I'm executive director at Modulite and also leading the quantum business. Also, actually, I'm a chair of enabling technologies at QADC, so working with a few US companies on that. A little bit about Modulite. So we are a publicly listed company that was founded in the year 2000. And we are fully vertically integrated. So we start with the substrate, we build the lasers, and on the medical side, we build devices that the doctors are using in the operating room. So we build everything in-house. We have a lot of tools in our own fab. We can make semiconductor lasers, fiber lasers. We also have CNC machining for creating systems, electronic software, and so forth. ISO 9001 for quality, 14001 for environment, and also 13485 for medical device manufacturing. So we take the quality and the laser, let's say, functionality really seriously, because obviously when you're doing cancer surgery, you cannot have the laser die in the middle of that. And I guess several of your quantum companies also feel that the laser shouldn't die that often as they might. So we are developing in-house several technologies that fit quantum. We build DPR lasers, VCSELs, fiber lasers, and with these we can cover basically all the wavelengths from UV to 2 micron plus, can also cover different line widths from kilohertz to megahertz and powers from milliwatts to watts. And we can integrate all of these lasers into subsystems that can be integrated into quantum computers. We call it the ML6600 platform. And then that brings low noise drivers, electronics, and optics. So here's a little bit background why we need different laser technologies. This is just a sample of some of the wavelengths needed for barium ion systems. So you can see here that depending on the wavelength that you need, some technologies fit that better than the others. And here's a little bit more why we have chosen those specific ones. So we started in the years 2000 with the semiconductor fab. That's our bread and butter. We've added the other technologies later. But with these kind of DPRs, you can get to a couple of 100 kilohertz line width, get hundreds of milliwatts of power, can amplify that further with tapered amplifier. But if you want to go more to, let's say, low noise laser operation, then VCSEL is a really good solution. It cannot cover all the wavelengths needed, for example, by that barium, but it can cover several. And with this VCSEL, you can get to even sub-kilohertz line widths. You have a really excellent beam quality, tens of nanometers of wavelength tunability in contrast to, let's say, DPRs, watt level output, which enables frequency conversion. And that's why you can reach several of these otherwise challenging wavelengths. And then finally, there are fiber lasers, which we also built these in-house fully from scratch. And you can go from kilohertz to hertz type of line widths with these, very low frequency and intensity noise, and again high power in the, let's say, watt scale. And to sort of complete, here are a couple of our recent measurements for Ytterbium. So these are a couple of DPRs at 935, at both of them at 150 milliwatts. This 935 at 205 kilohertz line width, and then the 760 DPR at 275 kilohertz. And we will be at Photonics West, booth is 1267. So happy to talk with you all there, or also, of course, answer any questions that you might have here.
Yeah, we have plenty of questions. I will come back to you. But before that, the presentation by Aitan from Single Quantum has resonated with Icarus Quantum. Pollard, all the way from Colorado, tell us what's on your mind.
Yeah, thanks for the presentation. I was wondering, I saw that you have a dead time of about 10 nanoseconds for your detectors. And can you go down to maybe 1 nanosecond while keeping the high efficiencies?
Oh, this is one of the issues, right? We want to get very fast, but also maintain the high efficiency. And I must say that we've made quite a few strides in the last year in that regard. What I showed in the slide, these are what we are, providing off the shelf. But in our labs, we already have things that might fit your needs more closely.
That's awesome to know. Yeah, let's catch up.
Pollard, you have to go to Delft and see the QTech and see the facilities of Single Quantum. You will be amazed. Sander, the founder, and me go way back, and I'm quite impressed with this company. This is one of the ones to watch in our industry. Pollard, there's many companies here who want to talk to you. Many people are telling me you're going to be able to have a lot of business here, but we're going to go back to Max. Max, you just saw the presentation from Modulite. You're looking for pulse lasers. Give us something else. Give us a bit more spec so we can see whether we can match your need.
About this, a tunable wavelengths pulse laser in either band. I've shown you different infrared ones. With the repetition rate somewhere between, let's say, anywhere between 10 gigahertz and 100 megahertz, we can probably work with any of those. With the pulse duration between 1 picosecond, maybe up to 5 picoseconds max. And you're talking about very low noise, pulse to pulse, and really nice temporal envelopes.
Ale is smiling. I think there is something in his mind. I think he wants to reach out to you. Marc-André La Liberté, bonsoir, Interaction. You are here at this meeting, also corporate member. You have a question for Max?
Yes, I have a bunch of people talking around me, but I'll try to do this quick. I'm just curious about the challenges, how you work around them.
Typically just a normal pulse laser. So we either buy them or we do some custom laser development.
Okay, so far you work with what you have.
So, well, we have different ones, right? So it's either like compact high subfire lasers or it's fiber-based pulse lasers. So they provide the stability. and the pulse qualities that we need.
You add some components around the setup, like optical filters and some dispersion
Yeah,
management.
there's additional elements, of course, to ingest the light, and depends on how tunable and flexible they are. So there's a kind of matching exercise between devices that we fabricated and the driving electronics and photonics that we have.
Max, as you can see here in this industry, we have everything that needs, and you said that you can address every band. We have also fantastic nonlinear crystals from Covation. Stuart Conver is in the room as well. But I want to ask you a question. For many years, we have been looking at photonic integrated circuits for many of your challenges. The next stage on quantum computing, we saw the pictures, obviously it's going there. We have some companies like Lionics, like LIGENTEC, like AMF in the room. Tell us one challenge for those. And don't say an isolator on chip. We cannot make it.
It's fine. It's fine. Make extremely low loss interfaces.
All the way from beautiful, beautiful Lausanne, Michael Heiserman, LIGENTEC. Tell us, what's on your mind?
We have very low loss circuits, and Max, you know that, and we have also spot size converters that minimize the loss between the fiber and the circuit. So our circuits, we have different thicknesses depending on wavelengths and depending on loss. You can go down below 1 dB per meter. So we are not talking about dB per centimeter anymore. We're talking dB per meter propagation loss. We have very low loss waveguides, and depending on which wavelength or what application you wanna do, you can have either a very high confinement or low confinement waveguide. That is all in an extensive PDK, and in that PDK also we have we are working on active integration, getting photodetectors and modulators on the chip with heterogeneous integration. And Max, for you, this very low loss spot size converters where you can put an SMF28 fiber directly butt coupled to the chip. There is probably some of customization done, but we have seen very low losses with some of our customers here.
Thank you very much, Michael. You were hosting the Quantum Industry Summit this year. All of us went to your home. I'm eternally thankful. Next year, well, 2024, we go to Bristol. The Quantum Industry Summit 2024 of Optica is at Bristol. Make sure you all go there, because this is the city where I studied, and it will be my pleasure to have all of you at that beautiful, beautiful city. But now we go to the next speaker. We can see the silicon nitride photonic integrated circuits work very well for quantum computer, because we can buy a quantum computer today based on silicon nitride peaks. Desislava Nikolova is here all the way from Enschede in the Netherlands to tell us about QUIX, quantum. The floor and the attention of everyone is for you.
Yeah, sorry, it's again in yeah, I have to make it.
It is Gorilla Glass clear, don't worry, looks fantastic.
Okay, perfect. So
you have to switch the displays. Go to display settings and switch the presenter view from the speaker view. There you go. You know the drill. I think you
know
it very well.
It didn't work. No, sorry. Okay. And do you see it now?
No, you have to go again, do the switching of the displays. And while you do that, I would like to say that I'm amazed by how many companies today are commercializing photonic-based quantum computers in the last 2 years. It's fantastic. Tell us, from Enschede, QUIX Quantum.
Yeah, okay, I will do it like this then, because otherwise it doesn't work. Is it okay for everyone?
Of course. Yes, go ahead.
Yeah. Okay. Sorry for this. So my name is Desława Nikolova. I'm leading the hardware research and development at Quick's Quantum, where we develop and sell photonic quantum computers. Yeah. Sorry, it doesn't seem to work. Yeah, I'm really sorry for that.
Don't worry, we can do this. We can make a quantum computer with 20 modes. Of course, we can actually change the slide. Do not worry, take your time. If you want, what we're going to do is I'm going to ask my colleague, Carmen Panos, to share the slides for you. Carmen, please open the presentation and share them all the way from beautiful Madrid, which I have heard is really cold today. Here in Washington, it's snowing. Carmen, are you with us? Or Puya, do you have the slides?
I'm looking for it. Let's see.
In the meantime, Carmen is sharing the slides already. Very well. Thank you very much, Carmen. Muchas gracias. This is Lava. All you have to do is next slide, and we go to the next slide. The floor is yours.
Okay. So can we go to the next slide, please? Okay. So just to remind you all, what is a photonic quantum computer? So the basic components there are the sources, which generate the photons, a processor to perform the interference and time entanglement, and the detectors to perform the measurements. So how a photonic quantum computer works is the qubits are actually the photons. They travel through the processors where you manipulate your qubits by interference of the photons, and then you perform the computation, in fact, by measuring the output states of your photons. If we go on the next slide, I have listed here some of the unique advantages of photonics for universal quantum computer. Well, one of the big advantages is that it is modular. Because we work with photons, we can easily guide them on chip where they can be manipulated, but we can guide them off chip via optical fibers. And this makes it scalable because in this way we can interconnect multiple chips. Additionally, if we need some components to work at cryogenic temperatures, because of this modularity, we can put only the chip with the detectors in the cryostat, and all the rest can remain at room temperature. So it doesn't require this heavy electronic equipment. As it's based on a mature basis, as we use photonics and optical fibers, we leverage the existing telecom technology. And as I said, most of it can be made to work in room temperature. It's based on integrated photonics. This makes it compatible with CMOS fabs, which makes it affordable and easy to scale to high volume. And unlike other qubit implementations, photons, they don't decohere fast. They preserve the information for a very long time. Even if now, if you look back at the start of the universe, you can still detect the photons. So if we go to the next slide, you can see that we are actually selling photonic quantum processors since 2020. And we have already sold more than 20 of them with 12, 20, 32, even up to 50 modes. In 2024, so this year, we plan to launch the special purpose quantum computer and to provide cloud access to them. We don't only sell processors, but we also sell full quantum computing systems. And we have already made the first sale to the German Aerospace Agency. And by 2027, we will deliver the first error-corrected universal quantum computer. And if we go on the next slide, of course, in quantum photonics, there are also some technology challenges. As been pointed out here, low loss is one of them, and we are working to solve this. Our current devices, they show 7 dB per meter. We can also measure in the lab 3 dB per meter, but we need to go below 1 dB per meter. Another big contribution to the loss, especially if we look into this modular concept, is the fiber to chip coupling, where we need to go below 0.1 dB per meter. And there it's, of course, not only the alignments, but also the, the foundries have worked to do to minimize the loss related with fabrication, polishing, and surface roughness. We need fast and low loss phase shifters. Of course, fast is easy. It is routinely done for telecom. You can reach gigahertz per second, hundreds of gigahertz per second. Low loss is also easy, thermal phase shifters. But combining both requirements and fast and low loss proves to be still challenging. But we believe with heterogeneous integration, we can solve this problem. For a universal quantum computer, we would also need light sources. Different types are available. We've heard, many here, several companies here on the market. And another big challenge is the control electronics and the detectors. We are actually looking now into developing single photon detectors with high efficiency, which can operate at room temperature. Even if the room is somewhere in Lapland or in West Canada in the winter with open window. And on the control electronics, there are multiple, I think we can reach gigahertz speeds, but the challenge there will be how do we integrate the electronics with silicon nitride, for example. If we go on the next slides, this will be my last slide. Thank you for having me here. And we'll also be at Photonics West, so you can come to talk with us there if you have more questions. Thank you.
Oh, thank you so much, and thanks for outlining what clearly what you're looking for. And we have companies in the room, many of them that can address several of those. Which one of them, next one actually, all the way from Zurich, Switzerland, the experts in photodetectors, Albus Optoelectronics Detector Mayer. Does your detectors tell us what you do and how your detectors can address the challenges that this is Lowell was talking about?
Yes, thank you, Polya, for the kind introduction. My name is Hector. I'm head of product development at Albus Optoelectronics. I hope you can see my slide. Everything fine?
Yes,
so
we can.
First of all, let me address, it's very impressive to see this community of engineers and scientists here to work on very innovative products, really tackling the challenges to generate and also to count for every photon without losing them. So Albus Optoelectronics can help you to find the right detecting solution. So you want to catch every photon you generate and you treat through your systems and don't want to lose anything. And so Albus is a Swiss-based semiconductor company. So we are focusing on design and manufacturing of high-speed, high sensitivity, long wavelength 3-5 photodiodes and avalanche photodiodes. And we are already in the business for a long time. So we have 20 years of excellence in manufacturing 3-5 photodiodes. So we have our own clean room facility here, Class 100 clean room in Rüschlikon, Switzerland, where we produce all of our 3-5 photodiodes. And our products range from telecom datacom, so very high speeds, to laser monitoring and sensing. And today specifically, I want to highlight the high quantum efficiency. So this is a high quantum efficiency photodetector, which has quantum efficiency above 95%, which results in a responsivity of around 1.2 ampere per watt. So this photodiode has a large active diameter, which simplifies the coupling to all those waveguide solutions manipulating the light. At the same time, capacitance is low, bandwidth is about 2 gigahertz, and we have very low down current of 60 picoamps. So another part which we can help the community with is with packaging. So on one side, we provide bare die chips, as is shown on the bottom left on this page. But we also do flip chip mounting of arrays. It's shown on the bottom right. This is an array of high quantum efficiency photodetectors on a background carrier, which would be perfectly suited for butt coupling into a waveguide. And so we are also at Photonics West this year. So if you have any questions regarding to high quantum efficiency photodiodes or avalanche photodiodes, or you just want to reach out for R&D activities, or talk about your custom photodiode solution, I'm there. Thank you so much.
Thank you so much, Hector. This is Love. I have a question for you. You're quick to selling. I mean, you've mentioned that you're selling lots of them. Can you give us some insight on what sort of markets and find applications you're selling these processors and computers to?
Yeah, so we have photodiodes. Our main market is obviously telecom datacom. That's where the biggest volume is. So it's not really for this community here, I guess. We also have high linearity RF photodiodes. So if you need high power photodiodes, as well as 3.5 photodiodes for FMCW LiDAR. So basically everywhere where you are in the long wavelength regime and you need high sensitivity or high speed, we have a solution for that.
Okay, thank you. And same question for you. This is Lava. Yeah.
Well, first, several of the companies here they have purchased our processors, so you can find them in data centers. Also, research groups in universities who are trying to test the quantum theories, developed quantum theories, and the foundations of quantum mechanics. They're kind of our customers. Yeah.
Okay. And another question for you. I mean, these photonic circuits basically require lots of calculations and simulations as part of it. What sort of solutions are you currently using for those? Like softwares for simulations and calculations. Are those coming handy for your applications? For your design?
So we are in the business of selling hardware. So our software, we develop some software here in-house, but we also collaborate with other people for other companies for simulation software. But if you're talking about algorithms, for quantum computing, then of course, as any quantum computing company here, we are very much interested, to have more applications of the quantum computers.
Okay, and I was talking about designing of the quantum of the photonic circuits, which and simulation of those, which brings me to our next speaker, who actually they make such simulators from QuantScience, Nicola Stra. Nicola, please share your screen and tell us what you do and how you can help these photonic-based quantum computing companies.
Yes. So hello, everyone. And yeah, my name's Nicola. It's really good to be here and really amazing to hear about this different applications and different approaches to the photonic-based quantum computing. We are a company that is actually kind of on two sides. So on one hand, we do support the development of hardware, of products. So product development, digital research and development, and so on. At the same time, we are also using quantum computers on our own and kind of our customers of quantum computing companies. The company QuantScience is based in Finland. We are a startup, a very fast-growing startup, and we have developed a platform, a simulation platform, which is using finite element methods to help the product development. But at the same time, we also are working on implementing the simulation on real quantum computers. So we have heard a lot about quantum computing for material science or for chemistry, but we don't hear as much about product development and basically not the finite element method, but that what would be corresponding to that in the quantum computing world. So we have actually succeeded in running real simulations on real quantum computers in 3D. The current focus lies on computational fluid dynamics, just because of the algorithms that need to be developed. So basically you can imagine at the moment it's kind of possible to calculate large models, large simulations in a couple of hours or something like that. But imagine with quantum computing, with quantum advantage, this will be actually possible to apply on like whole aircraft just in a couple of seconds. So this is kind of the exponential advantage that we are talking about. Or, for example, plasma fusion reactors, just calculate and simulate all the effects at the same time. Just to give you some impression, so these are the results of our simulations. So these are pretty simple simulations. It's something that you can do with every FM software available out there. But the difference here is this is quantum lattice Boltzmann method. The simulation shows spread of aerosols, and it has been done on a real quantum computer. So we are actually working with several of them, IBM, Continuum, just to mention some of them. So yeah, what you are seeing here is really the first, as far as we know, first application of simulation on the quantum computer. And if you want to know more, get in touch, discuss your application, yeah, just get in touch. We are also going to be at the Photonics West, booth 2658. Me and my colleagues from from QuantScience will be there. And yeah, we are happy to talk. We are happy to discuss either the product development side or the quantum computing side. Just reach out to us.
Thank you. And I was chatting with Nicola last week, and he went a little bit more in depth on what they are doing, and I was amazed. I was amazed, and this is something to look forward to and to see what they are doing. And I'm really amazed by all the technologies that the Optica corporate members and companies are bringing to, and the next company that will be presenting actually has a very intriguing technology, additive manufacturing for making the components, and we have Philipp Dietrich from Keystone Photonics, all the way from Germany in here. Philipp, why don't you share and let us know what you do and how you can answer the Optica question for us?
Yeah, thank you very much for having me here. Yes, I'm Philipp from Keystone Photonics, and what we do is we provide industry-proven products and fabrication service using additive manufacturing, so 3D printing. And this picture shows what we basically do. We can 3D print high precision optics on fiber arrays, but we can basically print anything which is possible, so freeform structures. We're very reproducible in terms of beam shaping. Now this, what you see here, is not a rendering, it's real. The next picture shows you the microscopy image, and you can see how precise we can shape and focus onto something. The focus here, what you see in red, is real. This is light. It's just what you see through the microscope, and we focus on Karlsruhe, Germany. That's where we're based. So this is unedited picture. Now, what is unique about us? We have very small structures. We can create very small structures, and we can make them ultra precise, ultra reproducible. You can see here an ant's eye, and that's a comparison of the structure. So they're so small, you basically never see them, but they're ultra precise. And we're proud to say that we're basically the only company that can do 3D manufacturing of microstructures and at the same time give you a sigma value of the photonic components we can provide. So this here, for example, is the mode field diameter of a 3D printed structure. It ranges from -5 to +5% for 250 lenses. So we can be in the 5 or even 6 sigma range of what our customers require for coupling. They would never realize this variation what we have. We're ultra precise, we're ultra reliable. We originally we're mostly working in wafer level testing. We supply probes to for wafer level testing, as you can see here, to companies like FormFactor. They do 12-inch wafer testing and other applications with it. We also supply to several 12-inch silicon photonic foundries. And now what we can give you, so now we come from wafer level testing for silicon photonic foundries. We're in manufacturing there and we want to transfer our knowledge to quantum application. We already started with it, and we can provide a complete package. So it includes 3D printed freeform structures, application-specific products. So that means in particular for cryo, 4K, we can do liquid nitrogen immersion of our products. Nothing changes. We can do cycling from room temperature to 4K, etc. We have a broad wavelength range extending from 530 to more than 2000 nanometers, so 2300 is possible too. And what we can provide to you are 3D printed microstructures, and that can pave the way to milli-dB coupling. Of course, we can also provide products for test and measurements, also at higher temperatures. So our underlying technology is the Sonata 1000 of Vanguard Automation, and well, that is an industry-proven machine. It works, and we turn this into product. So please contact us, and looking forward.
Philippe, I have a quick question for you. You hear from everyone in the room that they are looking for preserve as many photons as possible, low loss systems, low loss connections, and all of that. Can you make a comment on that? How do you help people save their photons, basically?
Yes. So if you want to couple a fiber into chip, which is basically the challenge, we can make sure that we 3D print optics with plus minus 20 nanometer accuracy, shape and alignment to the fiber core, and that allows you to ultra precise align light, shape light, align the fiber to the chip, and that allows to go to this ultra low coupling regions. When I say milli dB, I'm talking about 0.2 dB or below.
Okay, we have a question from Lithium, Amir Qadimi here. Amir, why don't you unmute and ask your question?
Yeah, thank you. Actually, Philip, it's thank you. I kind of asked this question in the chat, but I think from you. But what about the wavelengths? Is it suited for short? I'm sure it's for C-band and O-bands. This works. But how about the shorter wavelengths? I think it's pretty also important for the quantum people, like sort of neutral atoms and ion, which are working at often shorter wavelengths.
Yeah, so 530 works. Below that, our products are right now not suitable. So 530 is the limit. 780 definitely works. Everything between two. Yeah.
I mean, do you suffer from transmission wavelengths, or is it just?
Yeah, below 530 transmission. I mean, the process is not optimized for these wavelengths, so some absorption kicks in. So I'd say for the first steps, above 530 is what we're looking at. If there's a strong push, we will go below 530. We know how to do it.
Excellent.
All right, thank you all. And with that, I'd like to introduce our next speaker, all the way from Colorado, which is very cold now, and from the company that uses neutral atoms that uses trapped ions for quantum computing, Quantinium, and Laura Nugent will do the presentation. Laura, all yours.
Hello, good morning, good afternoon. Thank you, Leah, for the invitation. So Quantinium is a trapped ion quantum computing company. I am the senior R&D manager for lasers, optics, and photonics. So today you'll be getting a ion trap quantum computing presentation with an emphasis on optics and photonics. So at Quantinium, we believe we have the world's best-in-class hardware. So we build quantum computers based on these surface ion traps with what we call a QCCD architecture. So that's called a quantum charge coupled device. We have two H series, and the H is because we were formerly Honeywell Quantum Solutions. So Quantinium is a merger between formerly Honeywell Quantum Solutions and Cambridge Quantum Computing. And so I'm very much on the hardware side, on the optics, lasers and optics side. We've built multiple versions of our quantum computer, and those run as a subscription model. So people can send their algorithms and we run them. We have a technical team that runs the circuits on our quantum computers. So we have high qubit fidelities, 99.8 to 99.9% 2-qubit gate fidelities. And we also have another side of our business, which is best-in-class software. So this is the part that's formerly Cambridge Quantum Computing in the UK. And we have several software in the quantum algorithm development space offerings, and one is cybersecurity, the world's only quantum computing hardened encryption keys. We have Inquanto, which is a state-of-the-art computational platform for chemistry problems, and then Ticket, which is an open access architecture for developing quantum algorithms, which is hardware agnostic, so it can be run on any gate-based quantum computer. Okay, so here I'm showing on the top left here a physical implementation of a quantum circuit. So you can see lasers flashing on and off. You can see transport. So we rely on two very difficult things, but that sort of enable our quantum charge coupled device architecture, which is transport of ions on this linear ion trap. And then also all of the lasers and optics that do many of the quantum operations on our ions. So we use ytterbium-171 as our qubit ion, and we use a second ion, a barium-138 ion on our currently released quantum computers as a sympathetic coolant. And so we transport these ions around with a sympathetic cooling ion in tow. And as you can see here, what I'm showing is all of the internal electronic states of those two ions. We use lasers for ionizing the neutral atoms to make them ions, for cooling the ions, Doppler cooling, laser cooling, etc., for preparing quantum states, for shelving, for measurement, and then laser-based gates. So gates is how we entangle and encode quantum information onto the qubits. And so you can see here with the two different species of ions that we use, we have a lot of colors that we need in the photonics space. So the photonics tools that we have in place right now for our currently launched quantum computers are in the UV to near IR wavelength ranges. So these are all CW lasers, and they're on the order of 10 to 15 different colors, all the way from the UV to the near IR, and many different powers, depending on optical powers, depending on what state you're addressing and what needs to happen. So from 10 microwatts to sort of multi-watt optical powers. Right now, everything is done in sort of a bulk optics type space. So we have routing and splitting. So a single laser source is being, all right, just a minute, buddy. Sorry, I got a kid home from a snow day in Colorado today, so I'm trying to multitask here.
Feel free to bring him into the presentation.
Sorry, yeah, that's right. Yes, so we have a single laser source from 10 to 100 different channels. We need, of course, lots of frequency stabilization. We use optical cavities, frequency combs, AOMs and EOMs for on and off switching and addressing all of the hyperfine states in our ions, amplifiers and nonlinear optics, and of course, low noise detectors. And then eventually, all of these photonics tools, we will need some integration with ion trap systems. So here's a busy slide, but an overview of the photonics development that we've done in-house with key partners. We're certainly always looking for more partners. It's nice to see lots of folks that we've already talked to on this call, but we need, low loss waveguides and components for splitting and routing and bends, splitters, on-chip splitters, outputs of photonic chips that are lithographically defined. We've been dabbling in metamaterials with our partners at NIST Gaithersburg for sort of novel beam designs and other things. Of course, we have a lot of metrology setups to look at these integrated PICs, beam profiling, three-dimensional beam profiling. In addition to waveguides, we're looking at grating couplers, outputs on the chip, looking at beams precisely crossing at where the ion sits on the trap. So lots of metrology and lots of early development of sort of our photonics toolbox for all the things that we will need to scale our optical systems for the future. So the last slide here is eventually, of course, we want to integrate not only the photonics, but of course, I haven't touched at all on our control systems and our electronics, mechanical, all of these things need to scale. But since I'm particularly, and this conference is particularly fixed on the photonics, of course, we've developed an ion-based quantum testbed for photonics with very simple ion traps to test some of these possibilities of photonics layers on and integrated with the ion trap. We need fast turn, simple traps to validate these things. Of course, we need optical interconnects that involves fiber feed-throughs, fiber attached to the chip, etc., which we've heard about already today. A lot of these photonics chips and photonics layers will need to be either in vacuum or cryo or both. And we need high power handling. And we're optimizing all of the designs for our quantum operations. Stray light mitigation is a big concern. And then trap charging and top metal disturbances on our ion traps due to the photonics. And so with that, I will leave it on that slide and entertain any questions that there might be.
Thank you very much, Laura, for a fantastic presentation, and also thank you for your co-star for being there with us. We have a lot of questions in the room, but allow me to go to Canada, because this is the most beautiful time of the year to go to Canada. Shamak, thank you very much for being with us from CNC Microsystems. I know you want to help her on photonic integration. Tell us what's on your mind.
Sure. Yeah. Hi, Laura. This was very informative. Everything is really great. So I can't barely take a break from the seminar. I got one major question for you. I know that inherently ion traps and ionic quantum computers are very stable in terms of coherence time and all some other hurdles that we have with photonics. But what is the major problem with scaling, especially for miniaturization? Is there a major hurdle in this way of realizing a quantum computer that requires I don't know, breakthrough, or at this time we're just talking about engineering optimization? Thanks.
Right. So, the biggest challenge, and it sort of encompasses all of the different disciplines, is, we do need to scale our qubit number, of course. And as everyone does, but we'd like to scale our qubit number while not having to scale linearly with, say, number of beams, for example. This picture here that shows kind of the beams, free space over the trap. So we'd like to be able to scale our qubit number without having to linearly scale our number of beams. The same goes with electronic signals. So all of the electrodes that are on the trap here. And so we don't want to have, an order of magnitude increase in our electrode signals while we are, getting more qubits on the trap. And so we are making, more larger traps that can hold more qubits. And there are interesting ways to do that. As far as photonics, typically the biggest challenges are, while we, free space optics and bulk optics and those sorts of things are bulky and they take a lot of space. We are able to get very good precision with our frequency stability and our pointing stability and these sorts of things. And so we need to maintain, low noise lasers and optical systems in order to address these quantum states. And so to do that while also introducing photonic components, in the visible and especially is a big challenge.
Thank you very much, Laura. Another question is coming all the way from Switzerland. Amir from Thin-Film Lithium Metal Insulators, Lithium.
Laura, this is amazing. I was quite impressed. So actually, quick question. You have dealing with a lot of wavelengths. So from UV to near infrared. So which ones are you actually trying to integrate? I suppose you're not integrating all of them, right? Because especially the UV ones are ridiculously difficult, but visible and near infrared might be possible.
That's correct. Yeah. So immediately the plan is not to integrate all, 15 wavelengths. There are certainly ones that make sense to integrate first. And one of those is the gate lasers. So that is the Raman detuned system here that sort of addresses the quantum states and does the entanglement. And the reason for that is because the pointing stability here, I show like there's two laser beams crossing on the trap. And that position and phase tolerance of those, where those two beams cross, is very difficult to maintain, and it's very affects the fidelity of our laser-based gates. And so to have those photonically integrated on trap, then any other noise that comes from, you know, outside of the vacuum chamber or even inside the cold head is all kind of common noise on the trap. And so that's really
Let me address this, but first of all, just so you know, Amir is actually working very hard on assembling a consortium for some idea that he has in mind. Get back to him on that. But Laura, one of your challenges is frequency stabilization, and that's one of the challenges for everyone. I think you all know my friend Gabriel Thomas from Menlo System. How can you help Laura on the frequency stabilization?
Well, this is something that's basically Menlo's bread and butter, frequency stabilization. And Laura, we've met before. We were able to share a platform at the Laser Congress 2022. Yeah, I think Laura's well placed to understand frequency stabilization capabilities.
Did you bring one slide with you to show us a little bit of details on that? Yes.
I did.
Tell us.
So
everybody knows that Gabriel is a very big fan of Optica and that we are a really big fan of Gabriel.
That's very kind of you to say. Can you see my screen?
Crystal clear.
Okay, super. So basically, I'm Gabrielle Thomas. I'm from Menlo Systems, and we are headquartered near Munich in Germany. And we are known for our precision photonics tools that are enabling some of the most complex applications in the world. And of course, none more complex than quantum technologies, especially quantum computing. So I've just got a few things that I wanted to show today. So two major tools that we have in our toolkit are our optical frequency comb and our ultra-stable reference systems. So an optical frequency comb, for those who don't know, is a very special form of ultra-fast laser that has been stabilized within an inch of its life. And you end up with a spectrum that looks exactly like a comb that you might comb your hair with. And this can be used basically as a frequency ruler to take very, very precise measurements. The ultra-stable reference that we have is an ultra-stable cavity with an external cavity diode laser that's locked to it. And what we have done to enable the quantum world is to combine these two into a 19-inch rack system, as you can see just on the top left-hand side there. And that is a fully integrated system, frequency comb locked to the ultra-stable reference. And then the frequency comb is used to discipline whatever CW laser is needed for your application. And we also have the ability to be able to integrate these CW lasers into the entire system. So basically all the end user needs to do is to think about that application. They get a fiber with the light coming out, or if it's UV, then we'll figure out a free space option for them. But basically it just delivers your comb disciplined light. And when I say comb disciplined, what I mean is we have a very, very narrow line width, typically a sub-hertz line width that comes out of it at pretty much any wavelength you want. And we've measured the fractional frequency instability of this, and it's down to about 10 to the minus 18 on the short term. I've mentioned here in these slides, well, my colleague Benjamin, who was supposed to give this slide today, unfortunately, he couldn't make it. He's prepared these few slides with example projects that we've been involved in to basically kind of give you an idea of the type of platforms that it can be used in. So the first is the Munich Atoms and the RIMAX project that's funded by the Federal Ministry of Education and Research here in Germany. Munich Atoms is a neutral strontium quantum computing platform. And RIMAX is a neutral ytterbium approach to quantum computing. We've talked about cold atoms here, but it's also our quantum laser system is perfectly suitable for trapped ion approaches. And we do also have another project, which is more of a photonics approach. That's a collaboration with Quant, where we're using basically systems, sort of integrated circuits type approaches. And we have a very compact frequency comb that's being used for that to enable basically the entire squeezing of the qubits. I've also mentioned a couple of other projects that are not directly related to quantum computing. First of all, SOLIS 1G. And the reason I'm mentioning this is because this is going to be a strontium lattice clock that will be in space. Now, for space, I don't think there is a more demanding environment to be able to develop technologies for this. And we also are aware that we need to have size, weight, and power restrictions to go up onto the rockets and so on. So we're developing much, much smaller combs and ultrastable reference systems to go into that. I think swap questions are also an issue in the quantum computing world. So this is something, there's no greater motivation than somebody who wants to integrate something or into their own quantum computing platform. So we're always open for collaborations and discussions that go further.
Thank you very much, Gabriel. I think many people are going to come to you. Basically, you have done, for many of our members, sub-hertz locking of light sources, and this is something that is very much needed on this network. But to close the meeting, I want to go to one company that has meant the world to me in my life. I want to go back to Enschede, this time to Lionics. You are working with many of the companies here. Many of them show challenges on integrated photonics. Send us off the way that we deserve. It's cold outside. Make us warm, Sadon. The floor is yours.
Thank you very much, Jose. This is a great introduction. So Linux International, it is also pretty cold out here, but maybe not as cold as everywhere else. We make silicon nitride chips and modules. We make chips for Quix Quantum. We make chips for ion traps for ETH Zurich. We make 780 nanometer lasers that are all integrated on silicon nitride. Quite a few things. That's one of the benefits of being in the business since 2001. We have, because of the broad number of applications that we're in, I'm going to focus only on a few things that I have pictures of here. These are all devices that we have made. For one, we have low optical losses that are in propagation and across interfaces. These are typically, we can get them lower than 1 decibel now, both in propagation, 1 decibel per meter, and insertion losses 1 decibel per facet. We also have pretty mature processes, mature enough that we can have an entire device be on 1 4-inch wafer. That's the one that's on the top right there. It's a great way to minimize interfaces, to have none of them at all. And then you can have 2,000 to 3,000 actuators on chip and then flip chip the entire wafer onto a PCB. Our experience is pretty interdisciplinary. We make stuff for space, for telecom, for sensing, for SATCOM. That picture on the bottom right there is a ceramic package for actually a satellite communication device that we made. And then we also have the entire visible light range accessible to our silicon nitride. It can cover from 405 nanometer to 2350 nanometer. So that's kind of the general stuff that we can do for everybody. We can design the chips, we can fabricate them in the clean room, we can assemble them into modules, we can package them as complete devices. And what I would love to have everybody here do is either you scan the QR code at the bottom right there to go to our website and have a look at some of our information, or come meet us at Photonics West, since so many of you are going. Thanks, Jose.
Yes, scan the code, and I would like to ask you very quickly, one challenge that you would like the rest of the room to help you with. That's the best way of closing the event.
I think the biggest challenge now is for us as photonic integrated circuit developers is to really hear the problems that are coming up next. We heard a lot about the making every photon count. We heard a lot about making everything scalable. Okay, past that, because we already have projects on these things, past that, what will be the next challenge? And if you can't come up with it here, then you can always come up with it and then send it by email to me.
And then you can, of course, collaborate with Optica as a platform to find ways of working together. I would like to remind everyone that if you want to get in touch with any of the participants today, all you have to do is send us an email, datepoto@optica.org, and we'll make the introduction. This meeting has been the result of very hard work by many people at Optica. The best thing you can do is to make sure that after this meeting, to get in touch with the people participating. All of you have received the participant list. All of you will have access to the recording of the video. Share it with your network. Make sure that we keep momentum, that we keep growing as an industry platform. I would like to acknowledge the Corporate Engagement Department team, and in particular, Ilya Dienat, Director of Peak Technology, and Cameron Panos, the Marcom lead for Europe. Until the next time, this was Jose Pozo on behalf of Optica. Thank you very much. Bye-bye.